At the shape of various compounds based on their arrangement of the atoms in space. We're also going to look at the hybridization of the bonds that occur with these specific molecules. And we're going to look at whether something is polar or nonpolar based on the difference in electronegativity. Now, VSEPR, which is short for valence shell electron pair repulsion, um, what we've found as chemists is that the atoms will arrange themselves accordingly to reduce repulsion. So the whole goal with a molecule is to find the sweet spot for the atoms to reside so that way you don't have repulsion between electron clouds. We agree that a covalent bond is shared electrons and they're negatively charged, and they figure out a way to coexist within that bond. But when you get multiple bonds together, they're going to push away from each other because they're similar charges, and they want to minimize that repulsion that they have with each other. Okay, so the thing that you want to do is you want to count the number of charged clouds. So that could be a bond or it could be lone pairs. And there typically is a central atom. So we're going to primarily look at the central atom and see what is the shape around that central atom. When you have multiple central atoms, you may have multiple shapes. And there's an example that we'll go through that shows that. Notice if you have a single charge cloud, we're talking about a single bond with two electrons within it. Now, if you see a double bond or a triple bond, we're going to count that as a single charge cloud. So even though they're sharing more electrons, it doesn't mean that they're multiplied by that number of electrons that they're sharing. So all of these items fall under a single charge cloud, and you need to be careful with that. Okay, so when we're looking at one bond, we could have a single bond, a double bond, or a triple bond. So we count them all the same way, even though they're sharing different electrons. We also say that if there is a lone pair, the lone pair typically is two electrons. Occasionally, you will see what we call a radical, which is a one paired electron. That's not the norm. Okay, so we typically, after counting the charge clouds, want to predict the shapes. Now there are 13 shapes, so it's good to take a look at the summary page of all these different shapes and know their names and know the bond angles for them. Okay, so here is an example where we have two charge clouds. So you would argue that carbon is the central atom, and on either side is one charge cloud. So when we have that, we consider it linear. Notice that on the central atom, there are no lone pair electrons. So that is not changing the shape at all. So as a result of it is linear. And you should know when you're talking about a linear shape, we're talking about a 180-degree bond angle. So notice that this is the ball and stick method, where we essentially just represent the bonds by sticks and then the atoms by balls. And notice that the bond angle is 180 degrees. Okay, here we have three charge clouds. This is our old friend boron trifluoride that we said has a suboctet. Notice that there is no lone pair above boron. There also is no double bond between boron and fluorine. We argued that this is the most accepted structure for this molecule. So there are three charge clouds. Notice there's no lone pair, and this is trigonal planar. Now, you have to be careful here because if you look at this, you could argue this is 90 degrees, okay? If we go by just the Lewis structure, yes. But the amazing thing is that boron and fluorine figure out a way to rearrange themselves so that they minimize the repulsion between the three covalent bonds. So trigonal planar is not going to have 90-degree angle. It's going to have 120 because that is the sweet spot where it minimizes the repulsion between the covalent bonds. Okay, so here is uh, NO2 minus ion. So notice that it has an overall negative charge, and the difference here is we have a lone pair electron that is above nitrogen. So we actually have three charge clouds. And notice that we're counting this double bond that is underneath nitrogen as a single charge cloud. Okay, so don't try to double the charge cloud based on that. So guess what? We have two covalent bonds or two bonding um, regions. We only have one lone pair. Now, this is the difference. We are not going to say that it's trigonal planar, okay? We're going to say that it's bent instead, and that's because of the presence of the lone pair. So you have to pay attention to the fact of how many bonds there are and how many lone pairs. So when we look at bent, um, it is 120. Um, so notice that the lone pair, they occupy a position in space that forces the covalent bonds away from it, and as a result, we have a 120-degree bond angle. So trigonal planar and bent share the same bond angle, but they do not have the same name. Okay, here we have four charge clouds. So we have carbon as our central atom, and surrounding that central atom, we have four covalent bonds, which we call charge clouds. So notice there are no lone pairs over the central atom, and as a result, we have a tetrahedral shape. Now, you would argue with this Lewis structure that there is a 90-degree bond angle between carbon and hydrogen. But the amazing thing is with the tetrahedral, it actually pushes itself into another shape, which is 109.5 bond angle. So this is the sweet spot that hydrogen and carbon coexist with, minimizing the repulsion between covalent bonds. So I would definitely know the bond angle 109.5. Now, here we have a different shape because the fact that we have, even though it's four charge clouds, the amazing thing is the lone pair above nitrogen actually forces a different type of shape. So even though there are four charge clouds, now we have one lone pair and we have a different shape as a result of it. So instead of calling it tetrahedral, we call it trigonal or trigonal pyramidal. Now, you are allowed to say that the bond angle is 109.5. If you look through some of the literature or online sources, they might say that it's slightly less, and that's because the lone pair does some amazing things. It causes the covalent bonds to be pushed away from it. And if you were to look at the space that the lone pair occupies as opposed to the covalent bonds, it's a slightly bigger region that it occupies because that electron pair repulsion is huge and it forces the covalent bonds down. Okay, here is another example where we have four charge clouds. So we have two covalent bonds and we have two lone pairs. So when we look at the shape of it, once again, even though there's four charge clouds, we can't call it tetrahedral. We have to call the shape bent. So notice that when you have the addition of lone pairs, the shape is different. So you got to be cognizant of that. So once again, the two lone pairs will force the covalent bonds to be pushed closer together. Now, you could say that the bond angle is 109.5, but if you go online and you look through some of the literature sources, they'll actually say it's even smaller, which is 104.5. So if you compare trigonal pyramidal versus bent, trigonal pyramidal, its actual bond is slightly less than 109.5, but bent is even more less than 109.5. Okay, here we go. So now we're back to molecules that exceed their octets. So notice that phosphorus is in the third energy level and it has access to d orbitals, so it can exceed its octet. So it's surrounded by 5 covalent bonds. And as a result of it, it has a different shape, which we call, instead of trigonal pyramidal, we call it bipyramidal. And once again, notice there are no lone pairs, so that is unique to this shape. Now, with trigonal pyramidal or bipyramidal, we actually have two different bond angles. So notice this is a side view, and if you were looking at the molecule at the side view, it does actually have 90 degrees between the central atom and its two charge clouds. But if you were to look at it from the top, notice that the bond angle between the central atom and the two charge clouds has a bond angle of 120. So yes, you would need to know these two different bond angles. Okay, here is a similar but different molecule. Once again, sulfur is in the third energy level. It can exceed its octet. And notice that it has a lone pair. So even though it technically has 5 charge clouds, one of them is a lone pair electrons. And as a result of it, it has a different shape, which we call seesaw. And once again, it's got 2 sets of bond angles. So notice that if you look at it from the side, it actually has 90 degrees. And if you look at it from the top, it has 120. So the good news is these 2 sets of molecules that exceed their octet, they have very similar bond angles. They just have different names. So I would make sure that you maybe make some virtual flashcards so you can get familiar with the different names. Okay, here we have 5 charge clouds, and we have 2 sets of lone pairs. So as a result, you might notice that there's a pattern here. We're going to have a different name, and this name is T-shaped. Notice that it's the presence of 2 lone pairs that causes this to have a different name. And notice that it has 90 degrees as its bond angle. Okay. Now, you could argue this is 180 degree based on the arrangement of the 2 atoms, but I'm assuming with AP they are just concerned with the central atom and its 2 charge clouds that cause it to have a certain bond angle. Okay, here is an example where we have 3 lone pairs. By the way, xenon, we talked about it before. Xenon and krypton are one of those 2 noble gases that are willing to actually form covalent bonds. And as a result of, we have xenon in the middle as our central atom. I have seen also iodine have this similar arrangement, so don't be surprised if you see iodine instead of xenon. So because you have the presence of 3 lone pairs, it's once again going to have a different name. Now the good news is this is an easy shape to remember. It's linear. So because it's linear, it's going to have a 180 bond angle. So the side view shows that the central atom has 2 charge clouds that form the bond angle of 180 degrees. And obviously from the top, it's not showing any other set of charge clouds that would form a bond angle. So you'd only need to know the 180 degree bond angle. Okay, here is once again sulfur, which can exceed its octet. Notice it has 6 charge clouds. So 6 charge clouds, no lone pairs. The shape is going to be octahedral. When you look at octahedral, thankfully it's 90 degrees either way. So side view and top view, it's 90 degrees. So that the good news is you don't have to worry about 2 different bond angles. So with the 5 charge clouds, obviously you have 2 sets of bond angles that you're going to need to know. Okay, here is an example of 6 charge clouds. So once again, you have 5 covalent bonds and a lone pair of electrons. And this, obviously, when you're introducing lone pairs, you have a different shape from the name. So no longer is it octahedral. And as a result of it, all of these are 90 degrees. So the good news is you don't need to worry about a second set of bond angles. Okay, so here is an example where we have xenon and it has 4 covalent bonds and 2 sets of lone pairs. So once again, it has to have a different name. So instead of the previous one where it was square pyramidal, this one is square planar. And here it has 90 degrees bond angles. I would argue with the side view, it also has 180 degrees. Okay, now I talked about in the beginning that you have to look at compounds with more than one central atom. So AP could give you a molecule that has multiple central atoms. And what you need to do is you need to pick one central atom and then identify the shape based on the cloud charges that surround it. So maybe carbon is the central atom, and you have to count up the number of bonds or lone pairs that surround it and then predict the geometry. Okay, so AP is really good at giving you organic molecules. This is an example of organic molecules. If we start on the left here, notice that it's got 3 charge clouds. This double bond counts as 1 charge cloud, okay? So if this has 3 charge clouds, it's going to be trigonal planar, okay? Now if you pick the central atom here, which is in the middle here, notice that it's surrounded by 2 charge clouds. So if it has 2 charge clouds, it's going to be linear. And then obviously for the other side, it's just the mirror image of the leftmost side, and it is trigonal planar. Okay, now we're moving into another section where atoms are really good at sharing their electrons, and they have to figure out a way to minimize the amount of energy needed to share those electrons. So what they do is they actually hybridize their way of sharing electrons so that it's equal. So it's sort of like you and a friend having chips and salsa. You figure out a way to divvy up the chips and salsa so that everybody gets the same share of chips and salsa. Atoms are really good at figuring out how to combine different orbitals, like the S and P. Remember the S and P? It figures out a way to combine those S and P orbitals and to divvy them out equally so that everybody gets the same share. Okay, so what is this? If you have 2 charge clouds, okay, you are going to use one S and one P orbital to give you a total of 2 orbitals. Together they're called SP, and notice that they have a 180 degree bond angle. Typically this occurs with triple bonds, okay, and you'll see more in a moment what that means. Now if you have 3 charge clouds around the central atom, notice that they combined 1 S and 2 P's to give them the sp2 hybridized orbital. And the ideal bond angle is 120. Typically you see this with double bonds, and you'll see more about that in a moment. And then lastly, you have 4 charge clouds. So you have 1s and 3p orbitals combined together to give you 109.5 degrees. And typically that occurs when you have a single bond. Okay, so you could argue here is a double bond, and as a result of it, this central atom here has 3 charge clouds around it. So because it has 3 charge clouds around it, it wants to have an sp2 hybridized orbital. So each covalent bond represents an sp2 hybridized orbital for that carbon. What does that mean? Typically you have 1 sigma bond. So sigma bond is a single bond where it has the sp2 clouds that are overlapping, and that's where they actually share the 2 electrons. And then if you ever see a double bond, you know that there has to be a pi bond associated with it. And notice that the pi bond is essentially 2 p orbitals that are perpendicular to the sigma bond, and as a result of it, the second set of electrons that are part of that covalent bond are being shared over with those p orbitals. I would make sure that you can identify this type of arrangement. Okay, now in organic chemistry, there's actually what we call cis and trans isomers. So whenever you hear isomers, they have the same formula. The only difference is they have different arrangement in space. Okay, and what happens is it's typically with a double bond. The reason why is it prevents the bond from allowing movement within the molecule. Typically, when you have a single bond, there's rotation around the axis, but if you have a double bond, there is not rotation around the axis. So that's where we have the introduction of cis and trans isomers. So here is an example of cis and trans. So notice that the CH3 substituents that are on the ends of these molecules, they're both facing one direction, and that's what we call cis. So cis, they are forming a molecule where the two substituents or the end chains are on the same side. Now we can have the opposite, where we have a CH3 substituent on one side, and then across from it is another CH3 substituent or terminal group, and it is frozen in place. There is no rotation. So if you were to take these two molecules and overlap them, you would see that they don't match up. So they actually are different. Okay. So we have a situation where we have two charged clouds. So we have one covalent bond here, and then we have one triple bond here. And carbon, what it does is it creates an sp hybridized orbital to share its electrons. So on this side is the sp orbital, and on this side is the sp orbital, and the overlap is causing the different bonds. But please remember, this is with a triple bond. In order for this to happen, the amazing thing is that the molecule creates one sigma bond, and notice that the one sigma bond is actually the sp orbitals, and they are overlapping. That's where you have two electrons being shared. And then you have two sets of p orbitals. So you have a vertical set of p orbitals, and then you could argue you have a horizontal set of orbitals that are sticking out of this drawing here. And you have two pi bonds that are overlapping, and that's where you have the 6 electrons that are being shared. So you have 2 electrons being shared in the pi bond, and then you have 4 electrons being shared in the 2 pi bonds. I hope I said that right. So one sigma and then 2 pi bonds with a total of 6 electrons. Okay. I don't know if I want to say too much about this, but obviously when you have a triple bond, we have higher bond energy, and that's something that you should remember from previous notes. So I would just make sure that you remember that. Okay. Occasionally AP will throw in some more organic molecules. Here is benzene. Benzene is C₂H₁. So don't worry about the name less, but AP is very good about giving you formulas. With this structure, it is a ring structure, and notice that you have overlapping pi bonds. You would argue there's little hydrogens that are stuck out of each corner here. These are alternating single and double bonds. Now, because of resonance, so this means that you can have double bonds that move around. So notice that this first structure on the left is slightly different than the structure in the middle because we have the resonance structure. So there should be a double arrow here to show that these are resonance structures. Now, to represent the electrons being shared within this molecule, we draw a circle, and that represents the delocalization of the electrons. So the electrons are actually being moved around constantly and fluctuating between these different carbons. Okay, so polarity. This is a subject that sometimes stymies a lot of students because they're not sure how to approach it. So hopefully with this set of notes, you'll be able to figure out the hierarchy or the way to determine whether or not something is polar. You should know that if you have a atom that is more electronegative than another one, that you're going to have an unequal sharing of electrons within that bond. So covalent bonds can have polarity. Notice that if you have something that's more electronegative, it's going to have a slightly negative charge. If you have something that's less electronegative, it's going to have more of a positive charge. So here is an example of a polar bond. If you were to look at electronegativity, you would know that chlorine is more electronegative than hydrogen. So as a result of it, the flow of electrons is going to be more towards chlorine than it is hydrogen. Now they're still sharing electrons within this bond, but you're going to notice that the electron density is going to be higher near chlorine. So what we do is we actually represent it with a little sigma symbol, and we call it sigma negative. So we're showing the partial negative charge that chlorine experiences. This is not exactly saying that it's a definitive charge, but it's just showing that because the electron density is greater towards chlorine, it has a slightly negative charge. I'm sorry, that's delta. Did I say sigma? I apologize. Okay, so anyways, what does this mean? We're looking for dipole moments, and dipole moments typically are represented by mu. Now, I'm not saying that you need to calculate this, but you need to be aware that if a molecule has a dipole moment, that means it represents the fact that it's polar. This is just a way that chemists are able to calculate polarity based on, they look at the absolute value of the charge and they look at the distance between the parts of the molecule. Okay, so you have to determine whether a molecule is polar. The first thing is you need to have the presence of a polar bond. So a molecule is not going to be polar if it doesn't have a polar bond. And also with that, you also need to see whether the shape has an effect on polarity. So here is hydrochloric acid, and notice that it has a polar bond. Because it is asymmetrical, and asymmetrical is key when you're trying to figure out if the overall molecule is polar, you'll see a separation of charge. So you'll see the delta positive and the delta minus, and as a result of it, you will know that the electron density is going to reside more towards chlorine. So you would argue that this is a polar molecule. Now, here is an example where you have to think a little more thoroughly with your situation here. You could argue that this is less electronegative than oxygen, so as a result of it, you should see a change or a presence of polarity. So notice that the electron density flows more towards oxygen, so as a result of it, there'll be a greater delta negative charge towards oxygen. But this is where it gets a little tricky. It's like having tug of war with your friend. So carbon is having a tug of war with oxygen, and as a result of it, it is equally being pulled on both sides. So what happens is this overall molecule is nonpolar because it is symmetrical and the dipole is being pulled in equal but opposite directions. So we get a cancellation of these dipoles, and as a result of it, there is an overall lack of polarity. So this molecule is nonpolar. Okay, now here is an example where you should know that oxygen is more electronegative than hydrogen. So as a result of it, this should have a slightly more negative charge, and there should be a dipole. And you could argue that there's a dipole with both of them. So notice that we have a delta plus with hydrogen, and here we have double the delta minus with oxygen because we get a reinforcement of the dipole. So what does this mean? This means that they do not cancel. The key piece here is asymmetry. The other thing is I tell people a lot that the presence of lone pair electrons is an indicator. It's not a for sure, but it tells the reader that, or the visual recipient, that there most likely is a polarity with this molecule. You still have to check and see whether or not there's a dipole. So notice that because the dipoles are in the direction of oxygen, there's a reinforcement and an overall polarity of the molecule. So we do not get a cancellation like we did with the previous one. And you could argue carbon dioxide. So think about it. Carbon dioxide is found in fizzy drinks. And we know water is a polar molecule. Does carbon dioxide dissolve readily in water? No. We have to force it in there using pressure, okay? So you got to think about, in real world, do you see these two dissolving with each other, okay? And that's a good way to reason out whether or not something is polar or nonpolar. Okay, here is our friend boron trifluoride. So notice that we've got no lone pair electrons here, but we should know that fluorine is more electronegative than boron. So we do have a dipole. And notice that this is interesting, okay? You would argue, well, they're all pulling in opposite directions. Ha, that's a clue. Okay, and there's some symmetry. So because we have equal but opposite directions of the flow of electron density, they're all flowing towards fluorine. As a result of it, we get a cancellation of dipoles. So this molecule overall is nonpolar. Okay, here we have another example where we have carbon tetrachloride. So carbon tetrachloride, you should know that chlorine is more electronegative. So that must mean that we have a series of dipoles. Now notice they're all equal and they're all opposite. So as a result of it, we get the dipoles canceling. So they're having a symmetrical tug of war with each other. And as a result of it, there is no dipole moment with carbon tetrachloride. All right, now, just to throw it in, and once again, people, remember, even though hydrogen in the formula is in the middle, it does not mean that it should be in the center of the molecule, okay? It's always on the periphery. All right, so yes, there's definitely a dipole towards chlorine. Now, I kind of differ with the way this is being drawn because I'm an organic chemist and I don't necessarily agree with what this person is drawn here. If you have a difference in electronegativity that is less than 0.5, you could argue that there's no dipole. So I kind of feel that these three arrows on the bottom shouldn't be drawn. Is there a little bit of electronegativity difference? Yes. I would say the greatest is definitely between carbon and chlorine. Now, the dipoles do not cancel. And the reason why is there is asymmetry. So you could argue it's symmetrical on the bottom, but you could definitely argue that there's no symmetry at the top. Now, this person has argued that all these arrows are pointing in the same direction. I would argue that definitely the molecule has a dipole because of the presence of chlorine. Okay, here is trigonal pyramidal structure of ammonia, and you would argue that nitrogen is more electronegative. So you would argue that there should be a dipole based on the fact that more of the electrons are spending time closer to nitrogen, and that there is a slightly more delta minus charge above nitrogen. And these atoms are experiencing asymmetry, which is another key feature. I would also argue the presence of lone pairs also enhances the fact that there is polarity. So definitely there is a dipole based on this molecule. Okay, um, diatomic molecules. So that would be hydrogen, oxygen, fluorine, iodine. Okay, um, if they come from the same group and they have the same proportion, they're going to share the same shape. Um, I don't know if there's anything else I want to add, but notice that you could have polar or nonpolar diatomic molecules based on what's going on. All right,